Okay, so let us start. We had finished finite dimensional spectral theorem in the first two lectures, and we had started off with compact operators and so on. We are in the process of proving finite dimensional spectral theorem for compact normal operators. So, as I had mentioned, we will start with spectral theorem for compact self adjoint operators and deduce the same for compact normal operators. Okay. So, let us look at the notes. So, we had started off with a proposition which is necessary. So, let us see, right. So, this has nothing to do with compactness per se. If A is a normal operator and lambda is an eigenvalue of A, then lambda bar is also an eigenvalue for A star, right, and these two spaces are same, kernel of A minus lambda and kernel of A minus lambda star. So, that simply means that if A acts like lambda, A bar has to act like lambda bar, right. That is the first part of the proposition. Reducing subspace means it is invariant under both A and A star, right. If A acts like lambda, A star acts like lambda bar. So, of course, it is invariant under both A and A star. The second one is if A is normal, then the distinct eigenvalues will give you distinct orthogonal eigenspaces, right. That is kernel of A minus lambda is orthogonal to kernel of A minus mu. Notice that this proposition has nothing to do with compactness, all these are general results which we will be using. The third one is if A equal to A star, that means A is self adjoint. So, that is something you can note. Then eigenvalues are real. Okay. So, let's go ahead. Okay. So, this is maybe lecture 3. Okay. Okay. So, we will prove these statements. Okay, that is our first aim. Since A is normal, okay, so is A minus lambda, right. So, A commutes with A star. So, A minus lambda will commute with A star minus lambda bar, right, that is trivial, and we have, this is something we did in the finite dimensional case, the same is true here as well, right. That is how you prove that if A acts like lambda, then A bar acts like lambda bar. So, A minus lambda H equal to A minus A star minus lambda bar acting on H, right. So, this we have seen that. So, this implies that kernel of A minus lambda, right. So, that means if the left hand side is 0, that means A minus lambda H is 0, that is H is in the space eigenspace corresponding to lambda, then H is also in the eigenspace corresponding to lambda bar for A star, right, equal to kernel of A minus lambda star, right. So, that part is easy. Okay, and of course, both the spaces are invariant, right. So, of course, both the spaces are invariant under A and A star, right, because they act like multiplication by scalars. Okay. So, that is the first one. So, that is fine. Second one, so what was the second one? So, let's recall the statement that if A is normal, lambda mu are distinct eigenvalues for A, then the eigenspaces are orthogonal to each other. Okay. So, suppose that A x equal to lambda x and A y equal to mu y, lambda not equal to mu, right. So, I am taking two eigenvectors which have distinct eigenvalues, right. Then lambda times x inner product with y. So, x and y are vectors in the Hilbert space, lambda is one of the eigenvalues. I look at lambda times x inner product y. So, this is equal to, so take the lambda inside. So, it is lambda x and lambda x is given by ax. So, ax inner product with y, which is equal to x inner product with a star y, right. But what is a star y? So, this tells me whatever we have just proved tells me that a star of y equal to mu bar of y, right. So, this is, so this becomes mu bar times y, mu bar comes out as mu because it is on the right hand side, I will have x inner product with y, right. So, I have lambda x inner product with y is same as mu x inner product with y, and that can happen only if x inner product with y is 0, right, because lambda and mu are distinct. Okay. So, this implies, so all this implies that x inner product with y is 0 because lambda is not equal to mu, right. So, that tells me that the eigenspaces corresponding to different eigenvalues are orthogonal to each other, right, because A is a normal operator. See, so the last point in the proposition, if that is easy, if A equal to A star, then we want to show that the eigenvalues are real, right. So, eigenvalues for a self-adjoint operator should be real. Okay. So, Ax equal to lambda x. So, let us say A equal to A star and Ax equal to lambda x, then well A star x equal to, we just saw that this will have to be equal to lambda bar x, but this is A star is A. So, this is simply Ax, right, Ax equal to lambda bar x. So, implies lambda equal to lambda bar, right, x is never 0. So, you have a eigenvector which is non-zero, right, implies lambda is real, right, that is easy. Okay. Now, our aim is to prove the spectral theorem. We started with this auxiliary results. Okay. So, we will continue with so if you go back to the finite dimensional spectral theorem. So, let us take few minutes to understand that part. In the finite dimensional spectral theorem, what we managed was, if A is A star or A equal to let us say A equal to A star normal, it is actually self-adjoint, then with respect to a orthonormal basis, A was a diagonal matrix lambda 1 etcetera lambda n. Now, if you have a diagonal matrix, it is easy to see that norm of A equal to maximum of mod lambda j, maximum of the eigenvalues. Okay, norm of A as an operator on the Hilbert space Cn. Okay. So, what happened was, there was a eigenvalue whose modulus was the norm of A, right. So, now in the finite dimensional case, getting a eigenvalue was pretty easy, right, because we simply looked at determinant of A minus lambda I, that was a polynomial and it had a 0. So, that gave us a eigenvalue. In the infinite dimensional case, we need to show that there is an eigenvalue, and the way to show it is that we look at the finite dimensional case and see that it is the norm which is an eigenvalue. Okay. Well, norm or its negative, right, because if the operator is self-adjoint, either the norm or the negative of the norm should be an eigenvalue, that would be one of the lambda ones, right. So, that is what this whatever is written on the right hand side says, and we will try to show that. Okay. So, let me write down that. So, recall from the spectral theorem, in the finite dimensional case, that if A is self-adjoint, either norm A or minus norm A is an eigenvalue. Okay. So, we are going to prove that in the infinite dimensional case. Okay. So, let us, yeah, let us go to more. Okay. So, let us write it as a lemma. So, also recall that we'll use the result, we will use the result proved earlier, that if infimum of, so one way of finding eigenvalues was to write down the infimum of certain quantity and see if it is 0, right. So, infimum of norm of t minus lambda h, okay, where h was running over the unit sphere. If this is 0, then lambda is an eigenvalue, right, lambda is an eigenvalue. So, we will try to use this result. Okay. So, let's write it as a lemma. So, we will, as I just mentioned, our aim is to show that either norm to, so remember that we are assuming T is a self-adjoint compact operator. Okay. So, eigenvalues are real. So, we are trying to will show that either norm T or minus norm T is an eigenvalue. Okay. So, if T is a compact self-adjoint operator, okay, that is the assumption on T. If it is a compact self-adjoint operator, then okay, either norm T, so that's a value, or minus norm T, right, is an eigenvalue for T, is an eigenvalue for T. Okay. So, so once we get an eigenvalue, if you go back to the proof of the finite dimensional spectral theorem, you see that essentially the same steps will work at least up to some point, right, because you know that you can go down to the orthogonal complement of an eigenspace and then continue the procedure, right. That is what we did in the case of finite dimensional spectral theorem, and that same argument will work at least up to some point. We have to sort of finish it by collecting everything together. So, let's look at the proof. So, assume that T is 0, C is not 0, assume that T is not equal to 0 because there is nothing to prove T is 0. Then now recall that T is a self-adjoint operator, right. So, let me write down that since T is self-adjoint, the norm of T is equal to, because it is self-adjoint, it is enough to look at the diagonal elements, right. So, TH inner product with H, right, this, and you take supremum over norm H equal to 1. This was the value of the norm, right, because T is self-adjoint. Okay. So, since it is a supremum, you can take a sequence Hn from the unit sphere such that you have this convergence happening. Okay. So, hence there exists Hn such that norm Hn equal to 1, right. So, the norm of these vectors are 1 such that modulus of T Hn this converges to norm T. Okay. So, that is a that follows from the definition of the supremum, right, because it is self-adjoint. Okay. So, hence the sequence T Hn, well, where are these sequences? These are complex numbers, right. Well, T is self-adjoint, so these are actually real numbers. So, this sequence is bounded, right, the sequence is bounded. Okay. So, I have a sequence of real numbers which is bounded. So, there should be a subsequence which converges, right. So, let me, yeah, okay. Hence, there exists a subsequence which converges, but we are going to denote it by the, so I mean what I mean is we can go down to a subsequence So, by going to a subsequence, we may assume that the sequence Thn. So, strictly speaking I should write Hn k. So, instead of making messy notation I say that this converges to some value lambda such that mod lambda equal to norm t, right. So, I have first this sequence T h n and then take the modulus that converges to norm t. So, that tells me that T h n inner product with h n is a bounded sequence in the real numbers, and so it has a convergent subsequence. So, instead of calling the convergent subsequence h n k etcetera, we just use the same notation. Okay. So, it is h n itself, okay, just to simplify the notation. Okay. So, now we can continue. We have got this limit. So, we will show that this lambda we have got here is an eigenvalue. We will show that lambda is an eigenvalue, okay, for t of course. Okay. So, let us see how that is done. Now, norm of t minus lambda h n square. Okay. So, remember h n is the sequence we have looked at from the unit sphere, which has this property, right, T h n converges to lambda. So, t minus lambda h n square. So, let us expand this. So, this is equal to norm. So, this is easy, h n square minus 2 lambda T h n plus lambda norm h n square, okay, maybe lambda square, right, yeah, h n square, right. So, this is simply expanding the inner product, right, t minus lambda h n with itself. Generally there is a real part of something which is coming in the middle, but here you have a self adjoint operator. So, this is T h n is real, okay, which is less than or equal to, remember that lambda mod lambda is norm t, okay. So, this portion is less than or equal to norm t square into norm h n square, but h n has norm 1. So, this is less than or equal to lambda square, okay, and here this is equal to 1, right. So, I have a lambda square in the beginning, I have a lambda square at the end. So, I have 2 lambda square, okay, minus 2 lambda inner product T h n, okay, which of course goes to 0, because this is a sequence which goes to lambda, right, because of this. So, that means hence infimum of norm of t minus lambda h with norm h equal to 1, right, because of this h n's are unit vectors, right, and that is going to 0. So, this is 0, implies lambda is an eigenvalue, for t, right. That is the result we have used. Okay. So, let us go down. So, we have got one eigenvalue. Okay. So, lambda is an eigenvalue for t, and also remember that mod lambda is equal to norm t, right. It could be so either norm t or minus norm t. So, now we are in a position to prove the spectral theorem in full form. So, let us start with that. So, proof of the spectral theorem. Okay. So, recall that we are looking at only compact self adjoint operator. Okay. So, T is compact and self adjoint. Okay. So, I am not going to recall all the things statements in the spectral theorem statement we did some time back. As we go along, I will sort of explain each and every step. So, we can imitate what is there in the finite dimensional case simply by starting with an eigenvalue. So, if you go back to the proof of the finite dimensional case, you see that once you have an eigenvalue, you can look at the orthogonal complement of that eigenspace. You see that that is invariant under your operator, and you will have another eigenvalue there and continue. Okay. So, here the compactness is essential, right, otherwise you do not have an eigenvalue. So, if you just look at the lemma, we proved that you have an eigenvalue norm t or minus norm t, there we use compactness crucially. Okay. Okay. So, let us go to the proof. So, if T is compact, so some of the things are very easy to see, that non-zero eigenspaces are finite dimensional. Okay. So, let us see, if T is compact, let us write down here, if T is compact, okay, not necessarily normal or self-adjoint, okay, just a compact operator. From the definition, it is easy to see that any eigenspace of T, non-zero meaning corresponding to a non-zero eigenvalue, has to be finite dimensional. Okay, that is easy. So, the space X in the Hilbert space such that T x equal to lambda x, right. This is finite dimensional, is finite dimensional. So, let us call this eigenspace H lambda. Okay. This requires only compactness, you do not need any normality or self-adjointness. Why is that? Because restricted to H lambda, so T restricted to H lambda is equal to lambda times identity, right. On H lambda, it is simply multiplication by lambda, and compactness definition will tell me that this has to be finite dimensional, right. Identity is a compact operator only on finite dimensional spaces. Okay. So, so if lambda is non-zero, okay, so implies that H lambda is finite dimensional provided lambda is not equal to 0. Okay. This will be compact because T is compact, and this is the projection, you are restricting it to a subspace. So, it will have to be compact, and so it will be finite dimensional provided lambda is non-zero. The kernel can be quite big. Okay. All right. So, non-zero eigenspaces corresponding to non-zero eigenvalues are finite dimensional. So, that is one of the assertions from the theorem, right. So, that is taken care. Okay. So, now assume that T is compact and self-adjoint. Okay. So, and self-adjoint. Okay. So, we already know that. So, from whatever we have proved from earlier results, we have that there is an eigenvalue, right. So, norm T or minus norm T is an eigenvalue, Okay. So, let us call that, so that is the first eigenvalue, right. So, let us call that, so let us call that eigenvalue lambda 1, right, the first eigenvalue. Okay. So, what you need to note is that modulus of lambda 1 is norm T, right, because lambda 1 is either norm T or minus norm T. Okay. Okay. So, you look at the corresponding eigenspace. Okay. So, consider H1. So, that is the eigenspace corresponding to the first eigenvalue lambda 1. So, this is kernel of T minus lambda 1. Okay. So, remember that we are in the compact self-adjoint case, and this is finite dimensional, right, because lambda 1 is not 0, lambda 1 is 0, T is 0, right. So, we are looking at the non-trivial case here, right. write H equal to H1 direct sum H1 perp, right. So, the Hilbert space decomposes into H1 and H1 perp, right. Okay. Now, what we so this is what was the first step in the case of finite dimensional case. Once we found an eigenvalue, we looked at the orthogonal complement, right. So, now we have to look at H1 perp. Okay. So, since T is self-adjoint, self-adjoint, T of H1 perp will be contained in H1 perp. Okay. Well, this is true for normal operators as well, because the orthogonality will be preserved, right. So, if you want, we can check this. So, I take some y in H1 perp, I want to say Ty is also in H1 perp. How do you say something is in H1 perp? You check the inner product with H1 and see if it is 0, right. So, you take x in H1 and then you want to show that Ty is inner product with x is 0, right. So, what is Ty inner product x? This is y inner product with Tx. What is x? X is in H1, H1 is the eigenspace. So, this is simply lambda 1 coming out yx and that is 0, right, because y is in H1 perp and this is 0. Remember, lambda 1 is real, so it comes out as lambda 1 itself, not the lambda 1 bar. Okay. So, T takes H1 to H1 and H1 perp to H1 perp. So, T sort of splits, right. So, it is like when you diagonalize, that is the first you have the 1/1 element as lambda 1 and well, depending on the dimension of the eigenspace, you have that many lambda 1s on the diagonal and then whatever remaining is sort of orthogonal to it. Okay. Now, you can continue. So, clearly T restricted to H1 perp is self-adjoint and compact Okay. So, well, I will leave this as a question to you, but that is a trivial thing. So, when you restrict this to H1 perp, it is still going to be compact and self-adjoint. So, you can continue, right. So, hence there exists lambda 2, right. Remember what we did earlier, we got lambda 1, but there was a property of lambda 1, right. What was it? Modulus of lambda 1 was equal to the norm of T, right. Here the operator is T restricted to H1 perp, right. So, there exists lambda 2 such that mod lambda 2 is the norm of the operator restricted to H1 perp, right, and lambda 2 is an eigenvalue for T restricted to H1 perp, right. Okay. Also note that modulus of lambda 2, that is the norm of T restricted to a subspace, that is of course less than or equal to norm on the bigger space, right. So, mod lambda 1, okay, and lambda 2 is not equal to lambda 1, right, because if lambda 2 is equal to lambda 1, that is already contained in H1, right, but H1 is orthogonal to H1 perp, right. So, that is a trivial assertion. Okay. So, let us continue a little bit more. So, what we have got is, so now define H2. So, that is the eigenspace corresponding to the second eigenvalue. So, that is kernel of T minus lambda 2, right. Okay. So, this is going to be sitting inside H1 perp, right, and right. So, now we are continuing in the as in the case of finite dimensional situation, write the whole space H as I had H1 which was the eigenspace for lambda 1 direct sum, H2 which was eigenspace for the second eigenvalue lambda 2 and whatever is remaining. So, that is H1 direct sum H2 whole perp, right, the orthogonal complement. Okay. And then you do exactly what we did earlier, because H1 and H2 are eigenspaces, you see that T takes H1 and H2 to themselves and H1 directs some H2 perp to itself, right. So, it splits as earlier and you can look at consider T restricted to H1 directs some H2 perp, right. So, here you have this operator is self-adjoint and compact, right. So, you can continue this, right. So, I will stop with one line and then we will finish the proof in the next lecture. But what have we got? So, if you continue, to get, well, what did we get? We get lambda 1, lambda 2, lambda 3 and so on. These are eigenvalues. So, you can continue this. Properties of lambda i's are mod lambda 1, the first one has modulus equal to norm t and then it keeps reducing, right, because you are restricting the operator to smaller and smaller subspaces and so the norm will keep decreasing, right. So, we get continue to get 1, we will get lambda 1 whose modulus is greater than or equal to lambda 2 greater than or equal to lambda 3 and so on. Okay. Eigenvalue. So, these are eigenvalues of t, okay. Second one, if Hn is equal to kernel of t minus lambda n, that is the nth. Of course, the sequence in the first statement, that mod lambda 1, mod lambda 2 etc., that may be a finite sequence, okay. It can end somewhere and then what you have is only 0, that can happen. But otherwise you have a decreasing sequence of eigenvalues in modulus. Hn equal to kernel of t minus lambda n, the next eigenvalue, that is the lambda n plus 1. So, if you look at the way we got this, lambda n plus 1 was the norm of the operator, right. Though it had the property that the modulus of this is the norm of the operator restricted to whatever was remaining. So, that is norm of t restricted to. So, you take all the initial eigenspaces up to the first n, right, and you take the orthogonal complement, right. So, this was mod lambda n plus 1. Okay. So, what we have is a decreasing sequence in modulus of eigenvalues. We will show that it goes to 0 and if you put together all these kernels, that is essentially going to give you the range closure of T, okay, and what remains is only the kernel of T. Okay. So, you may have a huge kernel of T, otherwise it is a sum of these eigenspaces. And so, you can define this projection to these spaces and then show that when you sum up those projections with the weights are precisely those eigenvalues and you will see that you will get back your T. Okay. So, this is a statement which will look very similar to what you have on the finite dimensional case. Okay. So, we will stop here.